This is a solution to some of the problems on the section 2.5 worksheet that we didn't talk about in class. The first one we'll do is just practice 1, that's repeating example 1 but with a regular sized piece of paper. And so the diagram that's shown above, the little box that's there, the only difference will be that when we do this with a regular sized piece of paper, then the box won't have a square base. That's pretty bad. Yeah. All right, good enough. We'll still have x units will be the measurement of the little corner that we cut out, but now the dimensions of the box won't be square on the bottom. Rather, we'll be missing 2 x's from the 11-inch side, and we'll be missing 2 inches from the 8.5-inch side. When we fold it up, our dimensions will be 11 minus 2x, 8.5 minus 2x, and x. So it's really the same figure as this if you started with an 8.5 by 11 piece of paper here instead of 8 by 8. So in that case, our volume formula then will be similar to the one we did in class, but now the volume formula will not be as symmetric. It'll be the product of the 3 dimensions of the box. I said the word 3 as I was writing the word number 2 and screwed myself up. There we go. And so that's the volume formula. And so we need to do our optimization drill with this thing. We do have a limitation on the size of x, just like we did in class. X certainly can't be smaller than 0. 0 would reflect not cutting any corner out at all, which is certainly an option. And then in class we said the x couldn't be bigger than 4, because once you got to 4, you can't cut more than half of it out of each corner. And another way of thinking about that is that this dimension can't be negative, this dimension can't be negative. So when x is 4, that means this dimensions are 0, which I don't know how you interpret that, but certainly those can't be negative. And so the same thing's going to happen here. So 11 minus 2x can't be negative, so x can't be any smaller than 5, any bigger than 5.5. 8.5 minus 2x can't be negative, so x can't be any bigger than 4.25. So that means the limit is really 4.25, the maximum size that x could be. So if x is bigger than 4.25, then this picture doesn't make sense in some way. I'd have a negative number as a dimension. That's the way we think about it. Okay, so to take the derivative of this, we need a critical values, and so we usually take the derivative. This would be easiest to multiply this thing out first. This would just be FOIL, and you multiply through by x. It'd be fairly easy to do. If you do that and take the derivative, I just did it separately so I can just write down what I'm getting. So 93.5 minus 78x plus 12x squared. So this is my derivative. This is not the expansion. Right? So you can see when you expand this, you'll get like a 4x cubed. The derivative of that will be 12x squared. So I'm not writing down the expansion. I'm just writing down what the derivative is. And so the question is, when is that equal to 0? And that I do not believe factors, so I just used the quadratic formula and found that this happens when x is approximately 1.5854, or x is approximately positive 4.915. But just as the well, anyway, so we don't care about this one. We only care about ones that are reasonable values of x. So that's why we write this interval down in the first place. X being 4.9 doesn't make any sense. We wouldn't be able to complete this picture if x is 4.9. But 1.5854 definitely does. And so this is going to be the place where we have our maximum. It's easy to see that because if we followed our process, we'd go back and plug in our endpoints into our volume formula. But if you do that, you get 0 in both cases. So putting x equals 0 in here makes this 0, and putting x equals 4.25 makes this 0. So because v of 0 is 0 and v of 4.25 is 0, all we have to know is that v of 1.5854 is not negative, right? As long as it's positive, then that's the biggest point, since the other two options are 0. So if we do that, if we plug that in, we get a volume of is that, 66.15, and this is square inches. And so that's got to be our maximum. The other two options were 0, and certainly 66.15 square inches is bigger than 0. So that's the maximum volume that you can have. Now the question asks specifically, is this enough to hold 1 liter of water? And so we have to do a conversion there, but the conversion is this. So this is cubic inches. Every cubic inch is 16.35 cubic centimeters, and so we could rewrite this by multiplying the cubic inches times the number of cubic centimeters per cubic inch, and that's approximately 1,084 cubic centimeters. And 1,084 cubic centimeters is just a bit bigger than a liter. So there's a piece of trivia for you. If you were to fold up a piece of paper into a box, it holds roughly a liter, just a little bit more than a liter of liquid, if it was, I guess if it was waterproof. Okay. Problem 2, it's really exactly like example 2 that we did in class. So let's first parse our statement. We see the optimization word is right there. It says find the largest of something, and then we look for what is modified by that word, and that's area of rectangle, and so that tells us that we need a formula whose outputs are areas. Area of a rectangle is just the product of its two dimensions, and so that's pretty easy to see from my picture over here. Let me just make this bigger for a second. When we have a diagram, especially on a piece of graph paper, we want to label everything, and labeling on a graph like this is often comes from labeling the coordinates that you see. So for example, if I call the x-coordinate of this upper right point, use the letter x to stand for that, then the y-coordinate is just going to come from the formula. So 6 minus 3 halves x will be the y-coordinate of that point. And the value of x can be, the value of x could be 3.5 way out here, in which case the y-coordinate's right there, and we get like a little squat rectangle. The value of x could be like a half, like in here, and we get a tall, flat rectangle, tall, thin, skinny rectangle. So depending on what value of x you pick between 0 and 4, you'll get a different sort of shaped rectangle here. And the question is, which one of those has the largest area? Anyway, so I've labeled my rectangle's points, and the reason for doing that is because now I can label my rectangle's dimensions, which is what I want to know for the area. So the height of this rectangle is just the y-coordinate at that point. Right? That's what the y-coordinate tells us, is how far up to go to get to the point from the axis. And so that's exactly what we want to know for the height of that piece of the rectangle. Over here, I want to know the width. Well, the x-coordinate tells us how far over to go from 0. And so the width of this rectangle is just x. So now I have a labeled picture. It's easy to come back to my formula and say now the area is the width, x, times the height, 6 minus 3 halves x, of a rectangle. And I know the values of x have to be between 0 and 4, or I won't get a picture that looks like this. The only values of x that will make sense for this picture are x's that are from 0 to 4. And now, since I have this in terms of one variable, it's also my goal is to get something whose output is the thing I'm trying to optimize, but also has one variable in it. Now I can really call this a of x, or make up some function-looking name for it. Okay, and then I'm in good shape. Now I want to know what's the maximum value of this function on that interval, and I have a process for doing that. So step 1 of that process is find the derivative. Again, just like before, what it's easiest to do is to multiply this out and then just take the derivative using normal rules. But I'll have 6 minus 3x is my derivative. It's very easy to solve. 6 minus 3x equals 0 means that x is 2. And so that's the only critical value that I have. I also have the possibility that I could have max values at my endpoints. In this case, it's not going to happen, but it doesn't hurt to check. The reason it doesn't happen is because A0 and A4 both are 0. If you plug in 0 or 4 for x, you'll get 0 for the area. And when you plug in 2 for x, the critical value, then you get 2 times 6 minus 3, which is 6. So clearly that's the maximum of the three things, 0, 0, and 6. 6 is the maximum. And so that is the area. So that's the largest possible area, which is what it asks for. If it had asked for the dimensions of the largest possible area, I would need to go back and figure out what the actual dimensions of the rectangle are there. That gives me a area of 6. But that's also not hard to find. That's a 2 by 3 rectangle.